Alright, so welcome back to part 3 of thermal physics. And now we're moving on into the gas laws. When a gas is heated, pressure as well as its volume may change. To study the effect of temperature on these two quantities, we must keep one fixed while the other is changed. Two important temperature scales are the Celsius scale and the Kelvin scale. The Kelvin scale is known as a thermodynamic temperature scale or absolute scale. Be reminded that temperature in kelvins can be converted to degrees Celsius by subtracting 273, or you could just convert degrees Celsius to kelvins by adding 273. The volume temperature and pressure temperature graphs for a gas which are obtained experimentally are straight lines. They show that gases expand uniformly with temperature. It is believed that the lowest temperature possible is negative 273 kelvins, and it is referred to as zero or absolute zero. Any reading taken in kelvins has the unit K. They are exactly the same size as 1 Celsius degree. Near to absolute zero, strange things start to happen. For example, liquid helium becomes a superfluid. It cannot be kept in an open vessel because it flows up the inside of the vessel, over the edge, and down the outside. Some metals and compounds become superconductors of electricity, and the current once started in them will flow forever without a battery. There are 4 variables that are manipulated in the different gas laws: temperature, pressure, moles, which is the amount of substance, and volume. To see how one variable affects the other, we have to hold 2 variables constant. Now introducing Boyles Law and Charles's Law. Using absolute temperatures, the gas laws can be stated in convenient forms of calculations. So we have Boyles Law. Boyles Law: the volume of a fixed mass of gas is inversely proportional to the pressure if the temperature is unchanged, or the pressure of a fixed mass of gas is directly proportional to the inverse of volume. Here we have the equation where P1 V1 is equal to P2 V2. Charles's Law: the volume of a fixed mass of gas is directly proportional to its absolute temperature if the pressure is kept constant. And in this one, we have V1 divided by T1 equal to V2 divided by T2. Pressure law: the pressure of a fixed mass of gas is directly proportional to its absolute temperature if the volume is kept constant. So here we have P over T equals to the constant. Usually you will have P1 over T1 equals to P2 over T2. Then we have the general gas law. For a fixed mass of an ideal gas changing from state 1 to state 2, the following equation holds. These 3 equations can be combined to give P1 V1 over T1 equals to P2 V2 over T2. Please note, P and V may be in any unit of pressure and volume respectively, and that includes, for pressure you may have millimeters of mercury, atmospheres, torr, or Pascal. For volume you may have cubic centimeters, cubic meters, and anything cubic. Now T must be measured in the Kelvin scale or on the Kelvin scale. So if you're given units of degrees Celsius, you have to convert to kelvins. In problems where one of the variables is constant, it may be omitted from the equation. So if they tell you at constant pressure, then therefore pressure will not be included in the equation. If it says constant volume, volume will not be included in the equation. Same goes for temperature or amount of moles. At constant temperature, if the vessel is a very good conductor, any instantaneous rise or fall in temperature will quickly readjust to that of the environment. It can therefore be assumed that temperature is constant. At constant pressure, If the vessel is freely expandable, it can be assumed that the pressure is constant. Example, a balloon. Should the pressure instantaneously rise or fall, the vessel will expand or contract so that its contents have the same pressure as the environment, which is usually referred to as the atmospheric pressure. At constant volume, if the container is a strong solid vessel, it can be assumed that the volume is constant. An increase in temperature will cause a slight increase in volume of the vessel, but this is insignificant when compared to the increase that would have occurred if the gas had freely expanded. So here we can verify the gas laws using different setups. So for Boyles Law, which can be verified using the following setup, the pressure is increased by use of the pump, which you see right here. Okay? And the new pressure and volume readings are taken. About 6 readings may be taken. A graph of P against 1 over V may be constructed. Right? And so you will see the air column changing due to the pressure released on the oil. A straight line graph will be obtained and will verify Boyles Law. So pressure against inverse of volume will give you a straight line graph. Charles' law can be verified using the following apparatus. The air is trapped by the bead of sulfuric acid and is measured and recorded together with the temperature. The temperature is increased several times by about 10 degrees Celsius, and you'll be able to produce a graph of volume against temperature in kelvins. You should receive a straight line graph. The pressure law can be verified using the following apparatus. The pressure P and the temperature of the gas trapped in the spherical flask is measured and recorded. The temperature is increased several times by intervals of about 10 degrees Celsius, each time recording P and T readings. From this, you should get a graph of pressure against temperature, and a straight line graph will be obtained. This will verify the pressure law. Gases and kinetic theory. At higher temperatures, molecules translate at higher velocities, and therefore the rate of change in momentum, the force on collisions, is greater, where force is equal to mass times acceleration. The pressure therefore increases, so you have pressure equals to force over area. As a gas is compressed at a constant temperature, the speed of its molecules is unchanged, and therefore the force exerted by its molecules on the walls remains constant. Since volume decreases, pressure would increase due to collisions of molecules on a small surface area. As the temperature of a gas rises, the average kinetic speed of its molecules increases, and therefore the force exerted by its molecules on the walls is greater. If the vessel is freely expandable, the volume will increase, and therefore the area of the wall will also increase. The force and area increase by the same factor, therefore pressure will remain the same or constant. This is the kinetic theory of Charles' law. With the pressure law, the kinetic theory is such that as the temperature of a gas rises, average kinetic speed of its molecules increases, and therefore the force exerted by its molecules on the walls will be greater. If the volume remains constant, the area of the walls is constant. Since the force increases as the area remains constant, the pressure on the walls will increase. Now here we have questions. We have a bicycle pump contains 50 centimeters cube of air at 17 degrees Celsius and a pressure of 1 atmosphere. Find the pressure when the air is compressed to 10 centimeters cube and its temperature rises to 27 degrees Celsius. And 2. A diver releases an air bubble of volume 2 centimeters cube at a depth of 30 meters in water. Find its volume when it reaches the surface. assuming the temperature of the water is constant and that atmospheric pressure is 10 meters of water. So let's get started. Here we go. A bicycle pump contains 50 centimeters cubed of air. So we have the volume, the first volume, which is 50 cubic centimeters. And then we have temperature, which is 17 degrees Celsius, and we have to convert this to kelvins. And we have pressure equal to 1 atmosphere. And it says find the pressure when the air is compressed to, so we're looking for P2. And we have the volume is compressed to 10 centimeters cubed with a temperature of 27 degrees Celsius, say at 273. And so we're going to work that out. And we get 17 plus 273, that's 290 kelvins. And then here, +27 plus 273 will be 300 kelvins. And we're going to use this equation P1 V1 over T1 equals to P2 B2 over T2. And since we're solving for P2, we're going to just change it one time. So we're going to transpose, carry T2 over there, and carry V2 under here. So then we would have P2 is equal to P1 V1 T2 over V2 T1. And if we just substitute now, we put 1 atmosphere times 50 centimeters cubed times T2 300 K divided by V2 10 centimeters cubed times T1 290 K. This cancels, and so we know our answer will be ATM. And if we calculate, we will have 50 times 200, that's 15,000 divided by 2,900. And we got 5.2 atmospheres. Yay! Moving on, it says a diver releases an air bubble of volume 2 centimeters cubed at a depth of 30 meters underwater. So we could draw this. So we have here, we have the diver. We have the diver and the diving, and we have the scuba tank and something on the face. Alright, and the diving. Right, and they release a bubble that is 30 meters in the water. Alright, and then it's the finest volume when it reaches the surface, assuming the water temperature is constant and that atmospheric pressure is 10 meters of water. So additional pressure on that bubble of 10 meters. So if we write down everything we have V1 equals to 2 centimeters cubed at a depth. So the pressure is actually 30, P1 30 plus 10 meters, 30 meters plus 10, which gives us 40. Remember, pressure can be measured in distance or length, right? So yeah, you could use meters. And then we have V2, that's what we're looking for. And then we have P2. So by the time the bubble reaches up here, only atmospheric pressure is going to be acting on it. So the bubble is going to swim right up, and so only atmospheric pressure is going to be acting on it by this time. So it will be 10 meters. So since we have, this looks like Boyles Law, P1 V1 equals to P2 V2. We solving for P2, so we say P2 is equal to P1 V1 over P2. Right, guys? If we solve for that, we just divide both sides by V2. And we just substitute now. So P1 is 40 meters times 2 centimeters cubed over, oh, my bad, we're solving for V2. Oh, so this is V2. Let me just erase this. So we're trying to solve for V2. My bad. That's it. So solving for V2, so we're dividing by P2. So V2. So P1 will be 40 meters times 2 centimeters cubed over 10. Meters cancel out, zeros cancel out, and we're left with 8 centimeters cubed. That makes sense because usually bubbles get bigger as they reach the surface. They start out very small because of pressure from water and pressure from the atmosphere, right? And then they grow because they get larger by the time they reach to the top, simply because there's less pressure acting on it by the time you reach the surface. Great. Now, a gas is heated in a closed container so that its volume cannot change. Which of the following will not happen? So a gas is heated. Let me change the color. Ink color would be red. Okay. So a gas is heated. So here we have the gas in a closed container. 1, 2, let's put 6 molecules in here. So a gas is heated in a closed container so that its volume cannot change. Which of the following will not happen? The average kinetic energy of molecules will increase. It will increase because they're going to move up and down. Molecules will move in all directions. They will move in all directions. Number of molecules will increase. No, they won't. This won't happen. The molecules will hit the walls of the container more often. Correct. The pressure of the gas will increase. Well, I would guess that it will. If you heat it up enough and may cause an explosion. Yeah, because the container is not expanding to withstand the pressure that's building up in here. So definitely C. A container holds gas of 0 degrees Celsius. At what temperature must it be heated for its pressure to travel, assuming the container does not expand? Oh, I didn't even do anything for this. Okay, so a container holds gas at 0 degrees Celsius. So we have a volume. No, we have a temperature, sorry. Temperature of 0 degrees Celsius. To what temperature must it be heated for its pressure to treble, assuming the container? So I'm going to put pressure here as 1. I'm going to assume that pressure is 1 right here. Okay, container does not extend, so we're going to use P1 over T1 equals to P2 over T2. And we're looking for T2. So we're going to have T2 equals to P2 times T1 over P1. If we stick all of that in there, we see 3. I'm going to just say these are atmospheres. Just making it up. The atmosphere times T. So that's going to be 273 Kelvin. Because remember, we have to convert. And then over P1, 1 atmosphere. So then therefore it's going to travel. So 3 times 273, 819. So that'll be equal to 819 kelvins. Good. A gas occupies a volume of 100 centimeters cubed at a temperature of 27 degrees Celsius and a pressure of 1 atmosphere. Find the volume when the pressure is doubled at constant pressure. Find the volume when the absolute temperature is doubled at constant pressure and the pressure at 3 atmospheres and the Celsius temperature is 127. So I'm going to do us a favor. I'm going to create a page. We'll work this out. Okay, so let's try this. Can I use yellow? So the gas occupies a volume of 100 centimeters cubed at a temperature of 27 degrees Celsius. So from the get-go, let's just change 27 degrees Celsius to Kelvin. And that should give us 300, of course. So we know what this is. And we're going to list this. So the pressure is doubled. So a gas occupies a volume of 100 centimeters cubed at a temperature of 300 kelvins and a pressure of 1 atmosphere. Find volume when the pressure is doubled find the volume when the pressure is doubled at constant temperature. So we're going to ignore temperature then. This is constant temperature. So we're going to just look at PMV. So whenever we're dealing with PMV, we have a bunch of equations. We have Boyles Law, we have Charles's Law, We have Boyles Law, which is the pressure law right here. General gas law of P1 V1 over T1 equals to P2 V2 over T2. We have the ideal gas law. PV equals to nRT. But usually we just look at these four. That's right here. So we have here, we can just look at P1. V1 equals to P2 V2. Alright? And if we're solving for V2, we're going to have P1 V1 over P2 equals to V2. And that with substitution will give us 1 ATM times 100 centimeters cubed over P2 which is 2 atmospheres. And that will give us 50 centimeters cubed. So once the pressure increases, of course, volume would decrease. And in this case, you could see we have, remember, pressure is proportional to the inverse of volume. Right? The absolute temperature is doubled at constant pressure. So the absolute temperature. So let's go ahead, put this in. Find the volume. So we have V1 again equal to 100 centimeters cubed. We're looking for V2 once again. Then we have the temperature here equals to 300 K. And they said the absolute temperature is doubled at constant pressure. So we're not looking at pressure now. So the temperature is now doubled to 600 K. And if we use V1 over T1, if you look at it, you see this V and T we're using. So we gotta use this equation, okay? Because pressure is kept constant, so pressure is not gonna be present in the equation. Equals to V2 over T2, and we want to solve for V2. So V2 is equal to V1 T2 over T1. And substituting, we have 100 centimeters cubed times 600 kelvins over 300 kelvins. That goes twice. So of course the volume increases. Volume increases. So if you increase the temperature, the volume would increase. And now the pressure is 3 atmospheres and the Celsius temperature is 127. Find the volume. So we have V1. So from before we have V1 equals to 100 centimeters cubed. T1 equals to 300 kelvins. And P1 equals to 1 atmosphere. So now they're saying the pressure, we're looking for the volume, V2, the volume, and then T2 will be 127 degrees Celsius plus 273. And then P2 would be 3 atmospheres. So we treble the pressure, and let's see, 127 plus 3, and we increase the temperature by 100 kelvins. what's going to happen? What's going to happen to the value? Is it going to increase or decrease? It should decrease. So let's see. P1, B1 over T1 equal to P2, B2 over T2. And if you're looking for V2, then you can say V2 will be equal to P1, V1, T2 over T1, P2. Substituting 1 atmosphere times 100 centimeters cubed times T2, 400K over T1, 300K times P2, 3 atmospheres. The atmospheres cancel out. The zeros and the kelvins cancel out. And now we can calculate. So you now see 100 times 4 divided by 9. And did the volume decrease? Indeed it did. It's now 44.4 centimeters cubed, or 44. You could just round it off to 44. How amazing is that? So I hope this helped. And yes, my camera went off, but that's okay. We'll see you around for the next part of properties of matter. Do enjoy. Bye.